Hey guys, welcome back to my channel. Today we're going to talk about the selection sort algorithm. Selection sort is a fairly simple algorithm where you take the smallest element and swap it with the leftmost unsorted element. In this array, the leftmost unsorted element is 3. The smallest value is 1. We'll simply swap those. And then the result will be 1, 4, 7, 3, 6, 2, 5. Next, we start looking for the next smallest index, or the next smallest element, not index, and we'll swap with the leftmost unsorted element. This time, it's not the value at the first index, but rather the value next to it. So we'll have 1, 2, 7, 3, 6, 2, 6, 4, 5 as a result. Then next, we'll swap 3 and 7 because 3 is the smallest element and 7 is the element that is standing in its place, in the place of 3, where 3 is supposed to be. So we'll swap those and we'll have 1, 2, 3, 7, 6, 4, 5. Then we'll swap 7 and 4. Then we'll swap 5 and 6. Then lastly, we'll swap 6 and 7. I want you to pay attention to all the changes that have been happening step by step because they'll be important for understanding the implementation section. So now let's get down to the theory side or the implementation side of this algorithm. And what you'll come to notice here is that we still have the swap method that we had in the bubble sort video. If you're new to this video, just watch the bubble sort video where I explain how this swap method works. If you don't feel like going back there, I can just do a quick explanation. We're checking if I is equal to j. That if that is true, then we just return because we don't need to do any swapping, right? Or else we're going to set temp to the first element, we'll store that there, and then we'll change that element to the second element, and then we'll change the second element to the value of the first element, which was stored in temp. That's basically what we're doing. And now let's get down to the implementation. The first thing you would need to do is to check if you are able to grab the smallest element in this array, right? So you would set the min index to 0. So the index that has the value with the smallest, right? the index that contains the smallest value in this array. Basically, that's what I wanted to say. But so far we don't know which value it is, right? So we'll initialize it to 0 for now. And then we'll loop through this array starting at index 0. Actually, we're going to start at index 1, but I just want to explain later on why we're going to start at index 1. But I want to show you, I'm going to start at index 0 for now. So we'll say n length -1, we'll increment I, and then here we're going to check if n at index I, which at first is going to be 3, and you're going to try and compare it to min index, right? Min index is this. So now, if that is true, if this value here is less than the min index, right, that would be the smallest value in this array so far, you would set the min index to I, right? Whatever I is, if it's smaller than this value that we think is the smallest so far, then let's change the min index to whatever I is. That's basically what we're doing here. And then what I'm going to do is I'm going to print out min index, and you're going to see something interesting. Remember when I said you need to keep track of the changes that have been happening, like the first array after the first swap and all that stuff that we were talking about in the theory? Well, I'll show you later on something interesting. Okay, so far, as you can see, we get the value of 1 here. Just imagine if 1 wasn't here, we would get 2, right? So let's run that again, and we get 2. So that's basically how it works. So now that we can do that, we can actually swap the two values, right? We can swap the smallest value and the value that is at the first index. How do we do that? We make use of our swap method. We've already created that. And here we will pass in 0 because 0 is the leftmost index, right? And then we will pass in as a second argument min index. And I'm going to get rid of this print statement here. We'll run that again. And what you see here is 1473,625, right? What we did here is basically swap 3 and 1. Now 1 is at its sorted position. But here's another thing though. Here, the first thing we did is swap 3 and we first compared 3 to 3. We compared this element with itself. So yeah, that's not really optimal. But yeah, it doesn't make a lot of difference, but it's not optimal. If you want to really optimize this algorithm, you want to start at the next index, right? You want to make as few operations as possible. That's the whole purpose of learning about how about algorithm analysis and data structures and algorithms as a whole. You want to learn to optimize your algorithms as much as possible. So when I run this, it's still going to produce the same thing. It's not going to make any change, but it's going to perform less steps, right? It's going to perform less if statements, basically. Again, now we need to do like continue this whole thing again. We'll say second. I don't want to say pass, but second. Let's just say second. I don't know second what, but yeah, let's just say second. And then we'll change this min index to 1. And then we'll change this to 1. And then we'll change I to 2. Or we could say, yeah, we'll change I to 2. Right. So now 2 is sorted and the rest of this array is unsorted. We can continue this as long as we want and change the values. Do the swapping again, change the values to 2, change this value to 3, change this value to 2. It's gonna continue doing the same thing and it's gonna swap 7 and 4. Actually, it's gonna swap 3 and swap 3 and what? Yeah, basically whatever was swapped. Yeah, I think it's swapped 3 and 7. If I'm not mistaken, swap 3 and 7. Yeah. And what else are we gonna do? We're gonna continue the same thing over and over. We'll change this to 2. We'll change this to 3. So we're gonna continue this until the array is sorted. But then again, you can see where the issue is here. We're gonna need to write this code over and over and over. Like it's too much code, right? So we can use an outer loop to automate this whole process. So what I'm going to do is I'm going to remove all of this. So we could have continued this up until the whole array has been sorted. So I'm going to remove this. And what I'm going to do is I'm going to create an outer array. To the length of the array, increment I. And I'm going to refactor the I here so we don't have any issues to J. And I will cut that. Now we're going to need to make a few changes here. Remember, this changes from 0 to 1 to 3 to 4 every time. So let's just set it to I because I does the exact same thing. It gets incremented automatically. And we'll also change this to I. Right, so that makes our whole life easier. This one also increases, so let's set it to I plus 1. And when I run this code, we should get a sorted array. And as you can see, the array is sorted up until here and it doesn't sort the last element because this is up until length minus 1. So now let's run it again. Someone dropped something in the kitchen. That's why I laughed. But anyway, yeah, the array is sorted, as you can see. So this is basically how the selection sort works, right? There's nothing complicated about it. You basically just find the smallest element and swap it with the leftmost unsorted element. The time complexity of this algorithm is big O of n squared. Big O of n squared, like that. I mean, you would write squared the way you write it in a paper. Like, I don't know how to write it here, but yeah, this is how it is. Big O of n squared, which is quadratic time complexity. And as you can see, this is also a slow algorithm. And as you can see here, I've placed it in a package called slow algorithms. Yeah, so it is a slow algorithm. This is average case, the average case being the case that we have been working with now. The worst case would be when the array is sorted in reverse and we're trying to sort it the way that we have sorted it now. That is the worst case because it has to perform a lot more steps according to most algorithms, basically. But for this one, it really doesn't matter. It's still of big O of n squared. It's always going to be big O of n squared, whether it's best case, average case, or worst case. The best case is when the algorithm is already sorted. That is the best case. And I forgot to mention that in the bubble sort video, which was my mistake. The best case for the time complexity of the bubble sort algorithm in the best case is big O of n, which is linear time complexity.